Now, this tells us that it's very useful to count distance in standard deviations. And when you do that, you're counting in z-scores. You're converting the units into z-units. The z-score is normally distributed. It has a mean of 0 and a standard deviation of 1. Now, in practical terms, that means that when we're asked a question and we know that the mean is 0 and the standard deviation is 1, we can use z's instead of x's. Even if that is our random variable, we can think of it as z's. It is known as the standard normal curve. In other words, if z is allowed to range over its domain, it creates the standard normal curves for us. So before technology, when I was taking stats, we had these pull-out tables from the back of the book. We were allowed to bring them to exams, and our instructors looked at them to make sure that we hadn't written other stuff on them. But now we have technology, so we don't have to look up z-scores in a table. We look them up on our calculator. So here is geometrically what the standard normal curve looks like when we've got z-scores. I can use z if two things are true. If the mean is 0 and the standard deviation is 1. Okay, let's take a nice long look at technology. So I'm going to start by stepping you through the TI-83 as well as the 84, and then we're going to use Bell. So here's an 84. So let's turn it on and let us go into the distribution menu. So in the distribution menu under vars is the normal cumulative distribution function. So let's test this out. Let's go from -1 to 1. That is one standard deviation below the mean to one standard deviation above. And I know that those upper and lower limits are units of standard deviation because sigma is 1 and mu is 0. We're basically just checking the empirical rule, and it says that 68% of the data is between one standard deviation to the left and one standard deviation to the right of the mean. So in general, what this means is that we go into the distribution menu, that's second vars, we go to normal CDF, type in the lower limit, the upper limit, the mean, the standard deviation, and make sure you've got those commas in it. Now sometimes that's easy, and I always have students who prefer that over using Bell, but I prefer Bell. It's often, for me at least, more difficult to enter that than to simply use a program. Anyhow, I like programs. So Bell leads you step by step through the normal and also the student t distributions on both the TI-83 and the 84. It helps you select the built-in statistical functions. It's basically a user interface. It didn't add any functionality. Bell is simply there to help you find all these things. Now, one of the things that it doesn't take long to convince yourself of is that the TI is a very eccentric machine that does things in a weird way. I'm convinced that sometimes things are named differently just because they thought it would be interesting to do that. Now, the other thing that it does is it does inverse functions. Now, inverse functions are missing from the TI-83, so you do want to install Bell so that it behaves like an 84. Then a $12 calculator behaves like a $150 calculator. So here is the some calculator screenshots. When we get an example, I'll pull it up and show you how you get into everything. So let's say we're trying to figure out what this normal curve is, and we want to find an area under a region of the curve. So you might ask to find the probability that z is greater than 2. That is the probability that z is greater than 2, or z is greater than 2 standard deviations from the mean. So the program Bell not only allows you to find the probability that a random value selected has that distribution, but steps you through it. The first thing that Bell asks you is whether you want to find the probability or you want to find the boundaries. Now, you find the boundaries when you already know the probability. So that's actually an inverse question. It's saying, I know the probability, but I want to know what interval around the mean gave me that probability. So Bell is already telling us that it can do inverse probability questions. So we select 0. And it also allows you to work backwards, that is from the area of the probability to find the boundaries by selecting 1. So we're going to enter 0. And then we're going to enter 0 again, because in this case the data is normally distributed. When we have a normal, or when we have a student t distribution, we'll select 1. We have z values, so we will enter 1. X values are actual data that have a mean and a standard deviation that is different from 0 and 1. Then we're asked what the boundaries are. So we're going to select 1 because we're interested in the area to the right. Remember, we were interested in a z-score that was bigger than 2. So to be bigger than 2 is to be to the right of 2. So we choose 1 as our option for the region. Our z-value is 2. We type that in. We press enter, and out pops the probability. One interesting thing, if you want to reuse this probability for a calculation later on, it's actually in your calculator in the P memory position. So our next example is about male heights. So we're going to use x's instead of z's. We're going to do that because notice we are told the mean, so about 70 inches for the mean height, and also the standard deviation, 2.8 inches. So here we've got z values. In other words, their distribution does not have a mean of 0 and a standard deviation of 1, so we're going to use x's. So when it asks us, are we going to enter x values? Well, we're going to enter x values, so notice that we entered a 0 into the calculator, and then of course the mean and the standard deviation. So we want to ask the question, what is the probability that a randomly chosen blind date is over 6 feet tall? So to do that, we're going to say over 6 feet tall is to the right of 6 feet. So 1 gives us that choice. 6 feet is 72 inches, so our x value is 72. And then again, the result comes out of, or it goes into our memory location named P. Okay, so let's take a look at this in our calculator. So here's an 84. I'm going to turn it on, and I'm going to go into Bell. To get to Bell, you go into Programs. So it's installed, and I enter it to invoke it. Enter again. We've got, well, we were interested in finding the probability that a randomly chosen blind date is over 6 feet. So we want the probability. So we enter a 0 for the probability. This is normally distributed. Remember, we don't have to test or be told that height is normally distributed. We have the mean and the standard deviation, the population data. We're told that the population mean is 70 inches and that the standard deviation is 2.8 inches. We're now interested in finding the probability that that random variable x is greater than 6 feet. So greater than 6 feet is to the right of. So a 1 takes us to the right. To the right of what? To the right of 72 inches. That's 12 times 6. We'll press enter, and out pops the probability, 23.75%. Now our calculator also allows us to go the other way. So sometimes we know the area of the probability, and we want to know the values of x or z that traps that area, or perhaps excludes it on the left and right. Sometimes we even have an inside area that is centered about the mean, and we want to know what values trap that area. If these are z values, we can refer to them lots of different ways. We can refer to them as z star, z subcapital Z. That last one, z with a something over 2, that should be alpha over 2. So these are the critical values. The next question says, confirm the empirical rule for 95% of the data is contained within 2 standard deviations. So let's do that. So we're going to see where 95% of the data in the standard normal curve is. That is when we're dealing with z-scores. Standard normal curve. So to do that, let's launch Bell by going into Programs and invoking it. We are now interested in the boundaries. So we know the probability, 95%, and we want to find the boundaries. So I'm going to enter A1. This is a normal distribution, so I'm going to enter 0. And we're interested in z-values. That is the number of standard deviations that you have to go to enclose that much probability. So 1 means we're entering z-values. The probability is 95%. And we are interested in the inside area, that is to the left and the right symmetrically about the mean. So the inside area is 2. And it says that those boundary values are approximately -2 and +2. So notice there's some rounding there. And that those numbers count standard deviations. So the -2 means 2 standard deviations to the left of the mean. The +2 means 2 standard deviations to the right of the mean. So this is telling us that if we want to capture 95% of the data in a standard normal curve, we have to go 2 to the left and 2 to the right in terms of standard deviations of the mean. Okay, let's look at an example. The length of a human pregnancy is normally distributed. So we're told that we have a normal distribution. The mean is 272 days and the standard deviation is 9 days. Because we're talking about the random variable being other than a mean of 0 and a standard deviation of 1, these are x values. So what is the random variable? The random variable is the length in days of the pregnancy. So now it says find the probability of a pregnancy lasting more than 280 days. So notice that we can kind of do this intuitively. So let's start with that. So 272 is our mean. 280 is 8 days away from the mean. 8 days is slightly less than 1 standard deviation. Remember, standard deviation is 9 days. 1 standard deviation from the mean contains about 68% of the data. 1 standard deviation to the right contains 34% of the data. Everything below the mean is 50% of the data. So everything below 1 standard deviation to the right is 84% of the data. Thus everything above should be about 16. So you can kind of calculate through using the empirical rules. Or we can use a calculator. So let's do that. So we're told that the mean is 272 and the standard deviation is 9. Let's get Bell. So I'm going to go into Programs and invoke it. We're interested in the probability, so I'm going to enter a 0. This is a normal distribution, so I'm going to enter 0 again. We've got our mean and standard deviation. The mean is 272. The standard deviation is 9. So take a look at that to remind you that we're told it's normally distributed. The mean is 272. The standard deviation is 9. So with that data entered and checked, we can now say, well, what are we interested in? We're interested in this question of a pregnancy lasting more than 280 days. Well, more than means to the right. So the area to the right is 1. And we're interested in being greater than 280. Press enter again, and it tells us that the probability is about 18.7%. So according to our calculator, about 18.7%. So using that same mean and the same standard deviation, 272 and 9, we're going to answer these remaining questions. Find the probability of a pregnancy lasting less than 250 days. So let's go into our calculator and do this. I'm going to go into Bell. I'm going to launch it. We are interested in a probability, so 0. It's normal, so 0. We have our mean and standard deviation. The mean is 272. The standard deviation is 9. And now let's look at the question again. The probability of a pregnancy lasting Less than, well, less than is left of, just like in all of mathematics. So less than is left of, so we're interested in the area to the left, so we enter a 0. And we're interested in the area to the left of 250. We press enter and we see that this is not very likely, thank goodness. This is less than 1%, so about 0.7%. So when we go through and do this, we say that the probability that our random variable x is less than 250 is about 0.73%. The next question says, find the probability that a pregnancy lasts between 265 and 280 days. So we start the exact same way that we have been. We go into Bell, and we're interested in a probability, so we enter 0. It's normal, so we're entering 0 again. We've got our mean and standard deviation. The mean is 272. The standard deviation is 9. We are interested in being between these two values, 265 and 280 days. So we look at our options, and it looks like we've got an inside. So it looks like 2 will give us the area inside. The low value is 265. The high value is 280. And it tells us that the probability is about 59.46%, almost 60% of pregnancies last between 265 and 280 days. This next question is very different from the previous ones. Notice that it tells us a percentage. We already know a probability. Find the length of pregnancy that 10% of all pregnancies last less than. So we're interested in a boundary that separates 10% on the lower side from 90% on the upper side. So let's go through this again. A lot of things are going to be the same. So we're going to go into our program's Launch Bell. We are interested now in the boundary. Where is the boundary formed by 10% of pregnancies? So we enter A1. It's still normal, so a 0 for the next question. We still have the mean and the standard deviation, so a 0 for that question. These aren't z-scores, they're x's. The mean is still 272. The standard deviation is still 9. And we're interested in a probability of 10%, so 0.1. And we're interested in that 0.1 being to the left. So a 0 is to the left for less than. And it looks like that boundary is at 260 days. So let's see how to write that. We're interested in finding a boundary D such that the probability that x is less than that boundary D is 10%. And we've determined that that is approximately 260 days. Now, because this idea of working backwards is somewhat unusual, algebra is the art of restoring, of working backwards, so it does require an algebraic way of thinking. Let's go through and check this. Let's see what percentage of all pregnancies last less than 260 days. We're basically checking. So I'm going to do that with Bell. I'm going to launch the program. I'm going to imagine that 260 is correct, but I want to see what probability that is. So I want to compute the probability. I know that I have a normal distribution. I have my x values, the standard deviation and the mean, so I'm going to enter 0. The mean is 272. The standard deviation is still 9. I'm interested in the area to the left, that is less than. And I'm interested in the probability of being less than 260 days. And it's telling me that that is indeed about 10%, about 9%. So a nice quick check. Suppose you met a woman who said that she was pregnant for less than 250 days. Would this be unusual? And we have to say, since the probability of a pregnancy being less than 250 days is approximately 0.73%. That's definitely less than 5%, so we would say that it's unusual. Notice that we're comparing that to a question that we already did. We already asked the question, what is the probability of a pregnancy lasting less than 250 days? And we determined that that probability was less than 1%. And this fits our definition of being unusual. To be unusual, we have to include all values at least as extreme as that. So everything less than 250 as well. Remember, our mean is at 272. So 250 is to the left of our mean. So anything less than that would be more extreme. The next two questions look like they both have probabilities in them, so we'll be interested in finding the boundaries that contain that probability. G says, find the length of pregnancy that the middle 40% of all pregnancies last within. The middle means that we're bounded by the mean to the right and left symmetric of it. So let's get out Bell and let's figure out where the middle 40% of pregnancies lie in terms of days. So I'm going to go into programs. I'm going to grab Bell. I'm going to be interested in finding the boundary. So I'm going to enter a 1. Then I'm going to remind myself that this is normal, not a student t-distribution. It's got x values, days. The mean is 272. The standard deviation is 9. The probability that I'm interested in is 40%. And I'm interested in the inside area. This will be interpreted as the middle, so I don't need to worry about the symmetry of that. So 2 gives us the inside area, and there are boundaries, about 267 days to about 276 days. So let's state this. The probability that x is between the two boundaries, d1 on the left, d2 on the right, is 40%. Gives us boundaries of D1, that is the lower boundary of 267 days, and the upper boundary of 277 days. So I'll show you how that appeared on the calculator, our left boundary and our right boundary. The next question says, find the length of pregnancy for the longest 15% of all pregnancies. Here the key word is longest. So let's get Bell and let's figure out what that boundary is. So I'm going to go into programs and I'm interested in finding that boundary. I've got the probability. It says if you know the probability and you need to calculate the boundary, press 1. So I'm pressing 1. It's normal. We've got our x values, 0 for our x values. The mean is 272. You'll never forget that. The standard deviation is 9, and we're interested in a probability of 15%. And we're interested in longest. Longest is to the right, so I'm going to enter a 1. And it tells me that the boundary is 281 days. So we show this by saying that we want the random variable to be greater than some number of days to give us 15%. And if that boundary is 281 days, then 15% of all pregnancies are longer than that. Because this is such a large part of the course, we're going to go through another example just a tad quicker. Here we're talking about SAT scores. That's an intelligence quotient. So we know that it's normally distributed. Basically, that means that the data is normalized. The first question asks us to state the random variable. Here, x is the SAT score. We're asked to find the probability that a person has an SAT score over 700. So let's go into programs, let's launch Bell, and let's say, well, I want to know the probability that that person's score is over 700. We're told and we know that it's normal. We've got our mean and our standard deviation for the population. The population mean is 514. The population standard deviation is 117. And now we are interested in being over 700. Over is to the right. So 1 takes us to the right, over 700. And the probability of that is about 5.6%. So in symbols, the probability that x is greater than 700 is about 5.59%. Find the probability that a person has an SAT score of less than 400. So the same question, let's go through and do this again into programs, launching Bell. Let's find the probability. So a 0 for that first question. We know that it's normal, so a 0 for the second question. We've got our mean and standard deviation, so a 0 for the third question. We're now needing to enter the mean and standard deviation again. So 514 is the mean. 117 is the standard deviation. We're interested in being less than 400. Less than is left of. So we enter a 0 for that. We're interested in being less than 400. So our x value is 400. And it says that the probability is about 16.49%. So we write that as the probability that our random variable x is less than 400 is about 16.49%. Find the probability that a person has an SAT score between 500 and 600. So we're going to go into programs, we're going to launch Bell, we're going to compute a probability, we're going to use a normal distribution, we're going to enter the mean and standard deviation. The mean again, 514, the standard deviation, 117. We're interested in being between. Well, that's an inside area, so let's press 2. Now, because we're asked for a probability, that means that we need to know what those boundaries are. So in this case, the lower boundary is 500, and the upper boundary is 650. That will then tell us that the probability is about 42.5%. So the probability that that random variable is between 500 and 600 is about 42.51%. Find the SAT score that represents the top 1% of all scorers. So that means that we're interested in the 1% to the right of that boundary. So again, we're going to launch Bell. So we go into programs. We're interested in finding a boundary, so we enter a 1. It's still normal, so a 0 and a 0 for the next one, because we still know that the mean is 514 and the standard deviation is 117. And we're now interested in the probability. The probability is 1%, so 0.01. And we're interested in all of the top 1%. Well, the top 1% is to the right, so the boundary that gives us 1% to the right, an SAT score of 786. So the top 1% of all scores, where that boundary S is, X is bigger than that boundary S, is giving us a probability of 1%, is about 786 as an SAT score. Find the SAT scores that represent the middle 25% of all scores. So we're going to go into Bell. We're going to find a boundary. So enter a 1. This is normal, so a 0 for the second question and a 0 for the third question, because our mean is still 514. Our standard deviation is still 117. And we're interested in a probability of 25%. We're interested in the inside area. That will be interpreted as the middle area, symmetric about the mean. And so there's our boundaries, 477 to 551. So we're interested in the two boundaries that bound 25% of the middle scores. And it looks like that's an SAT score of 477 to an SAT score of 515. Last but not least, we're going to find the SAT score that represents the bottom 30% of all scores. So let's go into programs, launch Bell. We're interested in finding the boundary, so a 1. It's normal, and we have all the data for an X value. It's 514 for the population mean, 117 for the population standard deviation. We're interested in 30%, and we're interested in the bottom 30%. Well, that's the area to the left, so a 0. And it says that that boundary is at 453 on the SAT score. So let's see that. And that finishes our middle look at probability. So in 6.4, we're going to figure out if data that we're given is normal. Remember, in some cases, we're allowed to assume that it is. And those include height, blood pressure, IQ, and cholesterol level. But for everything else, we either have to be told that it's normal or we have to use the methods of the next section to assess whether that data comes to us as a normal distribution.